Hello. Today we are going to be looking at the chain rule. The chain rule is again given to us on page 25 in our log tables. Anytime we see differentiation, we always open up page 25 in our log tables, and it says dy dx, our derivative of our function, is given to us by dy du, so y differentiated with respect to u instead of x, and then what we differentiated by differentiated with respect to x. So y du times du dx is our chain rule. Again, that's on page 25. Where we use this is for composite functions. We've come across composite functions when we would have been studying functions in more detail, and it's where you would have f of g of x. So you have a function inside of a function. We're going to do the chain rule two different ways. One way is explicitly writing it out the way that we have here, and the other way is to say that we differentiate from the outside in. And both methods are very important to know. The first way we're going to go through it, the formal way we're going to go through it, is critical for when we come to the end of differentiation and we're dealing with things like related rates of change or implicit differentiation. So this method, the longer way, is extremely important to get a good handle on. But there's a much faster way of doing it that we also need to know in practice for simpler questions. So let's go and put this in practice. So we have y is equal to the square root of x squared minus 1. First thing I'm going to do if I want to do any differentiation is turn that into power notation. That's x squared minus 1 to the power of a half. Now I have something to the power of a half, so if I had x to the power of a half, I'd know how to differentiate that, but I have something that isn't x. I have x squared minus 1 inside of this function. So this is what we mean by a composite function. I have more than one thing going on, so I can't just differentiate it directly. So what I have to do is break this up effectively by a substitution. What I'm going to do is say that u is the bit inside here. So u is going to be x squared minus 1, the bit inside the bracket, or the function inside, and then the outer function I'm going to rewrite in terms of u. So y would be equal to, if u is this, u would be u to the power of a half. So I've defined what u is, I've effectively done a substitution, and I've said y is equal to u to the power of a half. And then what I'm going to do is use my formula from the log tables. dy du would be differentiating this with respect to u. So that's going to be dy du I'm going to differentiate with respect to u, so multiply by the power and subtract 1 away from the power. And then du dx is just differentiate this normally. So du is what u is what we're differentiating, and we're differentiating with respect to x. So multiply by the power and subtract 1 from the power. I end up with 2x to the power of 1, and my constant just goes to 0. So that's my differentiation done. I've differentiated y with respect to u, my substitution, and u with respect to x, like I'm used to doing. Now, I want to sub back in what my u was, so that I'm working everything in terms of x again, because u is just a substitution that makes differentiation easier. It's not the variable I want to be working with. So this is going to be a half on u is x squared minus 1. This is all to the power of minus a half. So now I have dy du and du dx. So dy dx is equal to dy du times du dx, as so. And then we just tidy this up. Now I have a minus power here, so I'm going to bring that underneath the line, and I have a half which is underneath the line as well. So this ends up becoming 2x all over 2 times x squared minus 1 minus 1 to the power of a half. I see I have a common factor of 2 top and bottom, so I divide that out, and I am left with x all over power of a half is square root, and that is my differentiation done and tidied up. So what did I do? I looked that I had a composite function. I defined what my u was, my inner function. I defined y in terms of u, and then I used my differentiation chain rule on page 25 in my log tables. I subbed into that, and I was able to simplify and get this. A reminder again, dy dx gives us the slope of this curve at different values of x, or the slope of the tangent to the curve at different values of x. Now, that's the formal way of doing that, and it's extremely important that we practice that a bunch of times because we will need it later on, and if we don't practice it now, it's much harder later on in the course. But there is a faster way of doing this, which we say is differentiating from the outside in. So that's what I'm going to show you now, and we want to practice both. So I start out with exactly the same function, just so you can see that they end up working out identically. What we do is differentiate from the outside in. What does that mean? Well, the thing that's furthest out is brackets to the power of a half. So I treat the bracket like it was just x. So if this was just x, I'd multiply by the power and subtract 1 away from the power. So I would end up with dy dx. I'm taking my derivative now, so this is no longer y. Multiply by the power. This is my x. Subtract 1 away from the power. Then I go inside, so I've differentiated the outside, then I go inside and differentiate what's on the inside. So if I differentiate the business that's inside the brackets, I have x squared minus 1, and if I take that, I have 2x to the power of 1 plus 0, and I multiply by the derivative of what's on the inside. So first, I took the derivative of what was on the outside of the bracket, treated it like the bracket was just an x, and then I went inside my bracket and differentiated what was on the inside and multiplied by that. So that's my chain rule, and it's chaining derivatives together. So I do the derivative of the outside and then multiply by the derivative of the inside. And I can do this for more complicated functions. I'll have to actually multiply several times. I won't always just be multiplying twice, because I could have multiple layers to my functions as they get more complicated. But the key thing is define everything as a power and then differentiate from the outside in. And if I simplify that down, I will end up again at x all over. You can see that this is exactly the same as this line, so it ends up being the same, x all over x squared minus 1, and we know how to simplify things like that. So this is vastly quicker, and we must know it, because otherwise questions like the one I'm about to do here would become extremely complicated and overwhelming. But this substitution method is critical for later on in the course, so we must practice it as well. But let's put this method here into practice in a more complex example, and we can see why we might not always want to do a full substitution. So if I have y is equal to x squared multiplied by the square root of 2x cubed plus 1, what type of thing do I recognize I've got? I've got a product. This is multiplied by this. So this is my u, and this is my v, and I'm dealing with the product rule. So I'm going to go to my log tables and write down the product rule when I recognize that I've got a product, two things multiplied together. So again, my x squared is multiplied by my square root business here. So I write down my rule, u dv dx plus v du dx. Define what my u is and what my v is. So u is x squared and my v is my square root, which I should write as a power, 2x cubed plus 1 to the power of a half. Write everything in power form all the time. I now have my u and v. I know that I need to get dv dx and du dx. So du dx is fairly straightforward. Multiply by the power and subtract 1 from the power. But we can see here we're going to need to use the chain rule in the middle of doing the product rule. So this is why doing an explicit substitution could get really overwhelming. This is why we want to have this simpler version for when we have this type of situation. So dv dx we're going to get as multiply, treat this bracket like it was an x, so multiply by the power, just write out the bracket as it was, subtract 1 from the power, and multiply by what is inside. So 3 by 2 is 6x, subtract 1 from the power is power of 2, and the 1 goes to just being 0. So I simplify this down. Simplify down your dv dx before you sub in. So this is going to be 6x squared all over 2 on the square root of 2x cubed plus 1. Same way as we move this around here. We recognize we have a common factor of 2 top and bottom. And we divide that out and we get 3x squared all over the square root of 2x cubed plus 1. So now we have done our chain rule business to get dv dx. We now have all of the things we needed to do the product rule. So now we sub into our product rule. U dv dx plus v du dx, and we simplify that down a little bit. We don't have to go all the way, because what we are primarily interested in, what the examiners are interested in, is can you get to this step here, but we need to do a little bit of tidying so we don't have a pile of brackets around. But we're not required to write, unless they ask you to explicitly, you wouldn't be required to write this as a single fraction. So that is my dy dx for this function. And even though this is a sum of terms and it looks all terribly complicated, always link back. This is the function that gives us the slope of the tangent to the curve, or the rate of change is the other way of saying that. The slope of the tangent to the curve, or the rate of change for different values of x. If I sub in different values of x, I will get the slope of this curve at that value of x. And that's what we need for the chain rule.